In this video, we're going to do a review of the gas unit that we covered. And gases are a bit different than solids and liquids in that they take up way more space for a given number of molecules, and the particles don't have the same impacts on each other because of that spread out nature that they have. So we assume that gas particles move in a straight line, smash into things, and they collide with the walls of their container and exert pressure. We assume that these collisions are elastic and they don't lose any energy as they collide because they don't stick to each other, which isn't entirely true, but that's the assumption we make. So they exert pressure on the walls of the container. The other features of gases that we can measure include volume and temperature, which kind of are more common language to us, but pressure is kind of different. We live in an environment where we have air molecules colliding with us all the time, but we don't really think of that because that's the medium in which we live. Anyway, ways that we can relate pressure to those parameters is through these three laws, or we can relate these parameters through these three laws. We have Boyle's law, which relates pressure and volume, and that's an inverse relationship. Because if you compress into a smaller container, decrease the volume of a gas without letting any air in or out, the pressure goes up. Conversely, if you let something expand, the density of these collisions goes down, so we're going to have less pressure. Gay-Lussac's law relates pressure and temperature. As you heat up a gas, the kinetic energy of the molecules or particles is higher, so they're going to collide with the walls more frequently and with greater force on average, thus the pressure will go up. So that's a direct relationship. Charles's law indicates that there is a direct relationship between volume and temperature. If you heat up a gas, it will expand because the particles are moving faster, pushing each other away more, so the density will decrease as the volume increases. And we can put all these laws together in what we call the combined gas law. Now, ways we can measure pressure. There's a bunch of different ways depending on what we're trying to accomplish. The simplest is atmospheres, basically taking at sea level, what's your pressure from the atmosphere, would be an atmosphere. But if we were using a barometer, if we had a 1 meter barometer, the mercury would get pushed 760 millimeters up the tube by 1 atmosphere, so we can use that as a way of measuring pressure as well. This is really the chemist's measurement for pressure. Then there's the physics measurement for pressure using kilopascals, and more commonly in America we use 14.7 psi to represent 1 atmosphere worth of pressure. Pounds per square inch is what that stands for. Anyway, so temperature, we don't want to use Celsius or Fahrenheit because Fahrenheit has negative values, Celsius has negative values, and Kelvin starts at 0, which is absolute 0, so it's actually a measurement of the kinetic energy. Notice we don't even use a degree symbol for it. All right, so other ways we can relate these properties for gaseous systems where we don't necessarily have the same number of moles of gas. These laws are for changing gas systems, where there's no new gas being added or removed, but we can describe any gaseous system statically through the ideal gas law, which we call PIV-NERT, which shows the inverse relationship between pressure and volume and the direct relationship with temperature with both of these things, and also moles. The more moles you have, the more particles you have, the more collisions you have, the more pressure you have, also the more space gas is going to want to take up. So there's a direct relationship there as well. Now, in this law, what allows us to relate these is the ideal gas constant, which we call R. And depending on what pressure system what pressure units we're using, there's a different value for R, and they're all listed there. Now, another adaptation of this law, or application of this law, is when we're describing gas density. Now, density for gases, we're going to use grams per liter instead of grams per milliliter. For liquids and solids, it makes sense to use mils because everything's so confined. Since gases are so spread out, we use grams per liter. And a sample problem I have right here would be determine the density of argon at this pressure and temperature. And when we're doing density, since density is grams per liter, the simple shortcut is to just assume 1 liter, and then we can use the ideal gas law and the values we're given to figure out how many moles we have. If we know how many moles we have, we can figure out how much that weighs. And then we would know how many grams that 1 liter would have in it. So we would say the density of argon at those conditions is 1.95 grams per liter. Now, another law that we learned about was Dalton's law, which applies to our atmosphere because we get all the pressure of the atmosphere from a mixture of gases. Some of it's nitrogen, about 78% of the pressure comes from that, almost about 21% from oxygen, a little less than 1% from argon, and then trace amounts of pressure from other gases, like carbon dioxide. Another application was we did a lab where we collected gas over water. And whenever you collect the gas over water, you're going to have some water vapor in the gas system. So not all of the pressure in the system is from the gas that we made. So here's a sample question right here. So if we did this lab, we made 8.5 mils of hydrogen gas at these conditions, we could figure out how many grams of magnesium reacted. So this is gas stoichiometry, incorporating Dalton's law as well. Because at that temperature, you're going to have a pressure of water vapor of 3.8 millimeters of mercury. So given that our total pressure was 765, if we're looking for the pressure of the hydrogen gas, we're going to subtract that water vapor from the atmospheric pressure to figure out our actual pressure of the gas. And then we can plug that into our ideal gas law to solve for the number of moles. And then once we know the number of moles of hydrogen gas, like any other chemical reaction we've done or any other stoichiometry problem, we can relate any two things in a chemical reaction as long as we use the molar ratios. And in this case, you get for every 1 mole of hydrogen we made, we used 1 mole of magnesium, and then we can figure out how much that weighs by using the molar mass. So that's kind of an overview of all the different problem types that we have in the gas unit and going over some of the properties and how they relate.